Hello, today I'm doing a video on stoichiometry. This topic is covered in both introductory chemistry and general chemistry, and it's typically a topic uh, that causes students to stumble a bit. So I'm putting together a video so my students can watch this discussion more than once, and so they can gain some understanding and review the material outside the lecture setting. So anyway, stoichiometry is all about, you have some starting material. You can talk about particles, you can talk about grams, both are good. And stoichiometry is all about getting your starting amount, converting to moles of your reactant, converting to moles of product, and then finding out your grams of product. You can go back and forth with this. And anyway, there's some fundamental concepts involved with stoichiometry that I'm going to go over first before I go into actual stoichiometry. So there's two fundamental concepts we need to understand before we can do stoichiometry. One is the mole, and one is the law of conservation of mass. So I'm going to talk about the mole first. The mole is a way of counting very tiny objects. I cannot handle one molecule at a time of some compound because they're just too small. I cannot pick up one molecule of water with my tweezers. It's just not going to happen. So the mole is defined as 6.02 times 10 to the 23 tiny objects. I'm calling this tiny objects because it can refer to number of molecules or atoms or ions. It's all good. And this number is called Avogadro's number. That's because Avogadro was a cool scientist-y chemistry dude who did lots of cool stuff, and so we're honoring him by naming this number after him. Because that's what we do in science. We name stuff after people we think are cool. So anyway, this relationship, we can use it as a conversion factor. I'm sorry, PowerPoint kind of barfed on my superscript here. This is supposed to say 10 to the 23. So like this does here. In any case, the 1 mole of something and 6.02 times 10 to the 3 of something is an equivalent amount. So if I have 1 mole of something, that means I have 6.02 times 10 to the 23 tiny objects. This is similar in using the word like, say, dozen. 1 dozen equals 12, right? So if I have a dozen of something, I have 12 of something. It doesn't matter what. I can have a dozen eggs or a dozen cars or a dozen pairs of pants. It all means 12. Same thing with the mole. I can have a mole of pants. I can have a mole of eggs. I can have a mole of hydrogen molecules. It all means 6.02 times 10 to the 23 of something. Now, I could say I have a mole of eggs, but I don't have a room large enough to handle all those eggs. So I'm not going to use it on everyday objects. I'm going to use the mole on tiny objects that I cannot handle one at a time because they're just too small, like atoms or molecules or ions. Right, onward. Okay, this is what a mole of something looks like. I can handle this amount, this quantity of stuff in my laboratory. I have here in the middle a mole of mercury. Got a mole of sulfur, I got a mole of copper, I got a mole of carbon. These are all quantities I can handle easily in the laboratory, and that's why I like using the mole. It's because it tells me how many molecules are present or how many atoms are present without having to count them one at a time because they're too tiny to count one at a time. Okay, so onward. Molar mass. The value of Avogadro's number was selected to make formula mass and molar mass match numerically. So for example, if carbon dioxide has a formula mass of 44.01 AMU, atomic mass units. Where'd my thingy go? Dang it. Oh well. So if the formula mass of CO2 is 44.01 atomic mass units, meaning 1 molecule of CO2 has a mass of 44.01 atomic mass units. I can use that same number to refer to a mole of something. So if I have 1 mole of CO2, it means it has a mass of 44.01 grams. So that this way, the molar mass allows me to find the mass of something, and it tells me how many molecules of CO2 are present without having to count them one at a time, because that would take me multiple lifetimes. So I know if I have a mass of 44.01 grams of CO2, the molar mass tells me that means I have 1 mole of CO2. I have 6.02 times 10 to the 23 molecules present. And I can use that as a conversion factor, which I have at the bottom of the page here. This 44.01 grams of CO2 is the equivalent, which is the same thing as saying 1 mole of CO2. And I can flip it and do that the same way. And I can use these conversion factors. Either one are good. It depends on what I'm solving for. If I want to solve for moles, I'm going to have mole in the numerator. If I want to solve for grams, I'm going to have grams in the numerator. Okay, this is just an equivalency here. All right, the next fundamental concept we need to understand for stoichiometry is the law of conservation of mass, which says that mass is neither created nor destroyed in a chemical reaction. So if I mix chemicals together, nothing's going to magically disappear or magically appear out of thin air. Everything I started with is still there at the end of the reaction. The atoms have just rearranged themselves to make something new. So here's my example here. Hydrogen reacting with oxygen to make water. I have a balanced chemical equation here. I'm assuming you already know how to balance equations in this video. Okay, so this tells me that if I have 2 H2 molecules for a total of 4 H atoms, and 1 oxygen molecule, which is the same thing as 2 oxygen atoms, because hydrogen and oxygen exist as diatomic molecules. That's their happy place. Okay, these guys react, I light a match, I get a lovely kaboom, and I end up with my water. And I have 2 H2O molecules. So you'll notice I have 4 yellow H's to the left of my arrow. I have 4 yellow H's to the right of my arrow, because nothing is magically disappearing or magically appearing. I got 2 red oxygen circles here and 2 red oxygen circles there. So everything on the left of my arrow appears on the right side of the arrow, just as the atoms have rearranged themselves to make something new. So hydrogen and oxygen have rearranged themselves to make water. All right, onward. Now we refer to this as the conservation of mass because my total mass on either side of the arrow is also the same. If I have 2 moles of H2, has a mass of 4 grams, and I have 1 mole of O2 with a mass of 32 grams, I will end up with 2 moles of water, which is a total of 36 grams. 4 plus 32 equals 36. The amount of mass on either side of my arrow is the same, because nothing's floating away and nothing's going, hello, here I am out of nothing. Doesn't happen. All right, everything on the left of the arrow appears on the right side of the arrow. And we get that by balancing our equations with our reaction coefficients here. And like I said earlier, I'm assuming you already know how to balance equations. Okay, but when you're doing stoichiometry, it's crucial your reaction is balanced correctly. If you're doing stoichiometry and your reaction is not balanced correctly, you'll get the wrong answer. Okay, because that law of conservation of mass always holds. That's why it's a law. It's not a suggestion. All right, onward. Now, when we look at some chemical equation, we can look at it 2 ways. At the microscopic level, meaning I have here the formation of ammonia. I have 1 molecule of N2 reacting with 3 molecules of H2 to make me 2 molecules of ammonia. That's the microscopic level. I can also look at the macroscopic level, which is like in a laboratory setting. So this reaction also tells me I have 1 mole of N2 reacting with 3 moles of H2 to make 2 moles of ammonia. Okay, so microscopic level, we're talking about 1 molecule at a time. Macroscopic level, I'm talking about moles of something. And remember, when we're talking about moles, it's all about counting. Okay, I could also say 1 dozen N2 molecules react with 3 dozen H2 to make 2 dozen ammonia. It's the same thing, just trade out the dozen with the mole and we're just counting. Okay, so the mole is all about counting objects. And the mole makes counting objects easy in a laboratory setting. Because the mole of something is something that I can do. I can handle that. All right, onward. Now we're ready to talk about stoichiometry. Stoichiometry is all about having some starting amount of some compound, converting it to moles of one compound, using your coefficients to use your moles of your product, and then you can end up with your grams of product using molar mass, or you can go from moles to particles, atoms, or molecules, either one, by using Avogadro's number. All right, so let's look at an example of a stoichiometry problem. Here in my next example, I've got octane, a major component of gasoline. I have a balanced equation here. I have 2 moles of octane reacting with 25 moles of oxygen. I'm burning it, right? And I make 16 moles of CO2 and 18 moles of water. I have a balanced equation here. Everything on the left of my arrow appears on the right of my arrow. I have 16 carbons over here, so I have 16 carbons over here, etc. All right, so our strategy for solving these stoichiometry problems is actually not that difficult. All you have to do is remember you got to go through the mole. You start with your mass of your reactant. You convert that to moles reactant. Use our stoichiometric relationships, which are given in our reaction coefficients here, 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 and here. All right, 2, 25, 16, and 8 are our stoichiometric coefficients. So I use these relationships to get me my moles of product. And then I use my molar mass to get my mass of product. So here's my problem over here. If I have 120 grams of octane and have lots of oxygen around, I can burn it all up, how many grams of CO2 will I make? And one thing I want to point out here, if I'm burning something in oxygen, it makes CO2 and water, and these are my only 2 products. This is complete combustion, which rarely happens in real life, but we like talking about it in chemistry problems because it makes things simpler and easier to assume complete combustion. If we had incomplete combustion, we would have CO2 and water and a gabillion other compounds. But here we're going to assume complete combustion because it makes life simple, right? So if, let's say, so I know here from my equation, if 2 moles of octane makes 16 moles of CO2, this relationship will always be true, 2 to 16. What if I don't have 2 moles? What if I have some different amount of moles? So in my problem, I have 120 grams of octane, which is not 2 moles. It's less than that. So I have something less than 2 moles, and I'm burning it in lots and lots of oxygen. How many grams of CO2 can I make? So here's my setup down here at the bottom of the page. I have 120 grams of octane. I'm going to divide by my molar mass. I have grams here and grams here that cancel, end up in moles. So I've gone from grams to mole. That's this guy here. Here's my stoichiometric relationship. I make 16 moles of CO2 for every 2 moles of octane that I burn. And that gives me my moles of product, but I'm not done. I want my mass of product, not my moles of product. So I'm going to multiply my moles of CO2 by the molar mass of CO2, and I get 370 grams of CO2. So this is your typical stoichiometry problem. You end up with start with the mass of something, convert to moles, convert that to moles of product, convert that to grams of product, and here you go. Ta-da! 370 grams of CO2. Now keep in mind when we do these calculations, this is what we call a theoretical yield. This is how much product I get if everything in the laboratory goes absolutely perfectly. And this is called a theoretical yield. This is the maximum product I can make if I don't have any losses or inefficiencies in the laboratory. So nothing's broken, nothing's leaking, nothing's sticking to the side of the container, there's no impurities to screw things up. That is my theoretical yield if everything is perfect. What you actually get in the laboratory is sometimes different. Sometimes you get a lot less, and that is our actual yield. The actual yield is a measured amount. You can't calculate that. Okay? And this will be less than your theoretical because you transferred something from one container to another. Not everything got transferred. There's droplets of something left behind, or you spilled, or there's a leak you didn't know was going on, or there's an impurity, or what have you. You get your actual yield as a measurement. You can't calculate that. It's a measurement. So when you get a problem discussing actual yields, the problem has to spell that out for you. You can't calculate that. Your actual yield will be part of a problem in certain stoichiometry problems. It cannot be calculated. It's got to be measured. All right, onward. So we can also talk about our percent yield. So percent yield is what really happened in the laboratory in relation to what could have happened if everything was perfect. So my percent yield is equal to my actual yield divided by my theoretical yield times 100%. All right, so let's work a problem. Let's say I have ammonium nitrate, and it decomposes to N2O in water. So in my problem, I start with 400.454 kilograms of ammonium nitrate. If I have this much ammonium nitrate, how many grams of water can I make? That's your stoichiometry problem. And in question 1, when I'm predicting how many grams I'm going to produce, that's a theoretical yield. That's going to be if everything goes perfectly. I don't lose anything. But in my problem, I'm also given my actual yield. If I actually make 131 grams of water, what's my percent yield? I cannot answer question 2 until I answer question 1. I can't get my percent yield without the theoretical yield, okay? That's right there. I gotta get that first. Okay, so here's what I'm gonna do. I'm gonna balance my chemical reaction. If it's not balanced, I'll get the wrong answer. Then I'm gonna determine my theoretical yield. That's predicting how many grams of water are produced. We're scientists. We love making predictions, right? That's what we do. And then I'm going to calculate my percent yield using my calculation from number 1 plus my information given in part 2. All right, onward. So we're going to balance my equation, and I do that by throwing a 2 in front here. So if I have ammonium nitrate, it will decompose to make 1 N2O and 2 waters. All right, I know I'm balanced because I have 2 nitrogens here and 2 nitrogens there, 4 hydrogens here, 4 hydrogens here, 3 oxygens there, 1, 2, 3 oxygens here, because that 2 applies to everything in the molecule. If I have a 2 in front, it doubles all of that. So I have 4 hydrogen and 2 oxygen there, okay? All right. So I balance my equation, so now I'm ready to predict how many grams of water I'm going to make from 0.454 kilograms of ammonium nitrate. Now, I don't want kilograms, I want grams, because that's what my molar mass is in. So I'm going to take my amount, multiply 1,000 to get to grams. Kilograms cancel, end up with grams. Now I'm ready to convert to moles and use my molar mass. 1 mole in the numerator, because that's what I'm solving for, and 80.05 grams in the denominator, because I want my grams to cancel. And I end up with 5.67 moles of ammonium nitrate. So now I know how many moles of reactant I have. Now I'm ready to figure out how many moles of product I'm going to get. And to do that, I need to use my stoichiometric relationships. I make 2 moles of water, that's where that comes from, for every 1 mole of reactant. There's an implied 1 there. Okay. When there's a 1 in our chemical equations, we don't put it, it's just implied. All right. So if I have this many moles of reactant, I multiply by 2, and I get this many moles of product, 11.3 moles of water. So I'm not done, I want grams of water. So I'm going to multiply my moles by molar mass of water, and I get 204 grams of water. That is my theoretical yield. I calculated that. If everything went perfectly in the lab, and all my ammonium nitrate decomposed perfectly, and I captured all my product perfectly, I would end up with 204 grams of H2O. That's my predicted theoretical yield. But in my problem for part 2, I didn't get that many grams. I got 131 grams. So that's my percent yield. So my percent yield is my actual amount, which is my 131, divided by theoretical, which I just calculated on my previous slide, times 100%, and I get 64.2% for my percent yield. And I am done with my problem. So to recap what I did, I had my mass of reactant that I converted to moles, and then I converted moles of reactant to moles of product, and then I converted moles of product to grams of product. And that was my theoretical yield, and that goes into my little formula here for my percent yield. So I went from grams to moles to grams to get my theoretical yield, and then I did my ratio to get my percent yield. All right, now sometimes we can have a reaction where we have too much of one reactant present and not enough of another. So if you have multiple reactants, it's kind of going to be likely that one of the reactants will be used up first before the others, and you'll have stuff left over from the others. That is called a limiting reagent, or also called limiting reactant. That's because when this reactant is used up, the reaction stops, it cannot proceed further, and you can make no more product. So your limiting reactant gets completely consumed, and the other reactants are just kind of left on their own, not doing anything, bored out of their minds. And these are called excess reactants. Whatever you have too much of is called the excess. So when you're figuring out your theoretical yield from this type of problem with a limiting reagent is what determines your theoretical yield. Because once your limiting reagent is gone, the reaction stops. You're not making any more. So you've got to figure out your limiting reactant in order to figure out your theoretical yield. So let's take a real world problem that we can do in the kitchen. Let's say you want to make cheese sandwiches. And each sandwich takes 1 slice of cheese and 2 slices of bread for every sandwich. Let's make a little chemistry equation out of this, because this is what we do. We're chemists and we love doing this stuff. For 2 slices of bread and 1 slice of cheese, I get my sandwich. Alright, so what if you have 10 slices of bread and 7 slices of cheese? You can only make 5 sandwiches, because you got 10 slices of bread. And you'll have 2 slices of cheese left over. The amount of bread determined how many sandwiches you made. You ran out of bread, you got cheese left over. So bread is your limiting reactant, and cheese is your excess reactant. Alright, now let's apply this idea to a chemistry problem. Let's say I'm reacting titanium oxide with carbon to make pure titanium plus carbon monoxide. My problem states if I have 28.6 kilograms of carbon, that's what reactant 1, and 88.2 kilograms of titanium oxide, is my other reactant, I'm going to get 42.8 kilograms of titanium. So, what's my percent yield? Well, I have to figure out my limiting reactant first, because that determines how much product I make. So first I'm going to figure out my limiting reactant. Once I've got that down, I can get my theoretical yield. And once I've got that, I can calculate my percent yield. Given this number, I was given my actual yield of 42.8 kilograms produced. Alright, so the first thing I have to do is convert my masses to grams instead of kilograms, because my molar mass is in grams, not kilograms. So I'm going to balance my equation, and here it is balanced, yay. 1 mole of titanium oxide reacts with 2 moles of carbon to make me 1 mole of titanium and 2 moles of carbon monoxide. So first I'm going to figure out my limiting reagent. First I have to convert everything to grams, so I'm going to multiply by 1,000 here. And then I'm going to figure out how many moles of each reactant gives me. So if I have this many grams of carbon, I have to convert that to moles of carbon. And then I use my stoichiometric relationship to figure out how many moles of titanium I make for all the carbon I have. And my relationship here is I have 1 mole of titanium produced for every 2 moles of carbon I consume, which is what my reaction tells me. So I multiply this all out, divide, yada yada, and I get 1.19 times 10 to the 3 moles of titanium. That is the maximum I can make of titanium if I use up all my carbon. So what about my other reactant? So what if I have this much titanium oxide, convert that to moles of reactant, and then convert that to moles of product I make. This is a 1-to-1 relationship, right? So I got 1-to-1 here. And I'm making 1.10 times 10 to the 3 moles of titanium. That's the maximum product I can make with this much starting material of titanium oxide. That's how much I make if it's all used up. Now I'm going to figure out my limiting reagent. I make 1.19 times 10 to the 3 moles of titanium from carbon, and 1.10 times 10 to the 3 moles of titanium if I use up all my titanium oxide. So the reactant that produces the fewest amount of product is my limiting reagent. This number is less than that number. So this is my limiting reagent, the titanium oxide. I'm going to use all that up first, so I'm going to have some carbon left over. Because if I had more of this, I could have made more product. Can't make that much. I could only make this, because this is how much titanium oxide I have. So this is my theoretical yield for my product of titanium, because this is my limiting reagent. But I want moles, I want grams. Let's move on. So here's my theoretical moles of titanium produced. I'm going to convert that to grams. There's my molar mass of titanium. I've got my grams of titanium. So now there's my theoretical yield in grams. Yay. So now we're ready to figure out my percent yield. I've given actual yield of my titanium in kilograms. I'm going to convert that back to grams, so my units are the same. So now I've got grams of actual product made divided by grams of theoretical product. Everything did not go perfectly in the lab. I made less than predicted. And so my percent yield is 80.9%. That is my percent yield for this reaction. All right, so that's it for today. I hope this helps. If you have additional questions, feel free to email me, and that is it. Thank you for listening.